Hello, this is Quick Precalculus Review for Calculus, Part 14, also Part 14 of a unit on comparing and contrasting linear and exponential functions. I'm planning on this video being the last part of that unit, so for Part 15 we're going to get into a new unit. We're still going to talk about linear and exponential functions, especially exponential functions in the new unit, but the focus will be different, not in comparing them. We're going to relate exponential functions to logarithms for one thing. We're going to talk about inverse functions in general. We're going to talk about different ways of representing exponential functions and ultimately get to something called the number e, which is a very important number in calculus and in math in general. We'll probably put all that in the context of thinking about compound interest to have a unifying feature, but that's the goal starting with the new unit, part 1 of the new unit. In this video, we're going to do quite a bit. You're going to want to, I'm going to go very fast. You're going to want to pause the video, have some note paper out to take notes whenever you can to try to understand things. I'm going to review the fundamental facts we've been looking at comparing and contrasting linear and exponential functions and give you a little hint about some calculus-related things. We're also going to talk about a couple of things in Mathematica that are new, something that you might call modular programming, which is essentially creating your very own commands or functions in Mathematica. And I'm also going to show you a fully formed animation for visualizing the unique linear and exponential functions through two arbitrary data points not on the same vertical line. Okay? You all set? We're going to go real fast here. Hang with me. Alright, we'll start by going down to this code that we focused on recently to animate the graphs of the functions 3 times b to the x, where b is an animation parameter that can change and give you different exponential functions, whether exponential growth or exponential decay, different values of b. I can also in this animation change the starting value of x and the amount that x changes by delta x, and we can see all these values over here. Okay, all this code up here, kind of complicated looking code, was needed to create all that. I want to start this video by showing you how to modularize this. What does that mean? That means essentially break it into more understandable pieces. I'm going to cut out this bit of code that creates the graph, and I'm going to give this code a name. What name am I going to use? Well, I see the first two built-in Mathematica commands that are needed for this code are show and plot. I'm going to go ahead and call this show plot. Notice that that is not black when I type that out. If I just typed out show or if I just type out plot, it would be black. But it's not, it's blue. That's because it's not a built-in Mathematica command. Show plot is a new command that I'm creating, a new function that is going to use all this code to create graphs. It's got to have inputs. It is a function, and in fact I'm going to have 3 inputs. One of the inputs I'm going to call g, and remember you've got to put underscores after variable names when you're first defining functions, and thereafter you don't. G is going to represent sort of an arbitrary function that goes in place of the f sub b's here. So I'm going to replace all these f sub b's with g's, which is a little strange if you think about it. I am plugging a function g into this function show plot. Plugging functions into functions. G is a function that you're going to graph with show plot. Show plot itself is just code that does all this stuff. What else do I want in here? I want an x and a delta x. Why? Because those are animation parameters down in this stuff here. Delta x, for example, is an animation parameter there. Outside the grid and the show, but inside the manipulate. They are the animation parameters. So I need to include them in here if I want to go ahead and take the show plot and replace it right there where I took all this code from before. Let's go ahead and enter this. I have now defined the command show plot. And now look, it turned black. Let me illustrate that it's doing the right thing by using it, for example, to make an animation of the graph of x squared as x and delta x change. So I'll put show plot inside the manipulate, put the inputs g, x, and delta x in the show plot. Ultimately, x and delta x are animation parameters. Let's say delta x starts at -5 and goes up to 5, and delta x starts at 1 and goes up to 3. This little tiny bit of code, based on the fact that I've done all this before, I've entered that, will now create an animation with the black graph being the x squared graph. And as before, I can change x, the starting value, and I can change delta x. Okay? So what I've done is I've modularized. Now I can take just this code, put it down here in my original animation in front of this comma, and replace the g with f sub b instead. It doesn't matter that it's f sub b instead of g. And I get the exact same animation as before. I can change b, I can change the starting value of x, and I can change delta x. And again, I can see all these things get affected. And then once again, the main point is delta y over y, the relative change in y, equals b to the delta x minus 1. That happens for exponential functions and not other kinds of functions. All right, next task here is to look at this example, a new example I've just made. Might be the only video where we look at it. Maybe I'll show it in another video. I want to create Mathematica code to define and then animate the unique linear and exponential functions going through two arbitrary data points, x1, y1 and x2, y2, where the y's are positive and the x's are not equal. And without loss of generality, we may as assume, assume x1 is less than x2. Here's the code that will create these functions, linear and exponential, to go through those two data points. Kind of complicated looking for the functions. Hopefully this first one is not too bad, and notice that I'm using subscripts here for the x1s, etc., and underscores, because those are going to be variables for the functions, but they're going to be animation parameters, and that's why I'm making them be subscripts. There's a conceptual difference there. This is essentially the equation of the line that you want in slope-point form, or point-slope form. Here's the slope, and the point is x1, y1. That goes there and there for the coordinates. I also could have used x2 and y2 instead, and I would get the same thing. So this one's a little bit more understandable, I think, to look at than this one. This is the exponential function. This is the value of a right here, and this is the value of b when you raise it to the 1 over x2 minus x1 power. I found those complicated expressions by solving this system for a and b in terms of x1, y1, x2, and y2. I would encourage you to pause the video and try that on your own. Okay? When you're back, you can look at the code and see that the code makes sense too. And we do indeed see, when we enter that code, that we have two arbitrary points that we can move around, change their coordinates, and we see a linear function, the red straight line, and an exponential function going through the 2 points. I have exponential and linear growth, or I could have decay as well. Okay? In all cases, the red graph is straight, of course, and the blue graph is usually concave up. The only time it's not concave up is when it's straight, when y1 and y2 are equal, when we're on the same horizontal line. All right, so I'll go back up here and show you the code again. You could pause the video if you want to look at it again. Try it on your own. Okay? Now we get to the main mathematical points to review the general principles that we've described before. First of all, here's the general principle for describing how linear functions change. We've seen this before. This is simpler than for exponential functions. If f is a linear function, then say f of x equals mx plus b, then delta y is proportional to delta x. For a given change in delta x, you can in fact determine the value of delta y by multiplying delta x by the constant of proportionality, which happens to be the slope m. Okay, and that's why we call the slope the rate of change. Think of an example here. Imagine x is miles traveled, and x is time in hours, and y is miles traveled. Then m, the slope, at a constant speed would be your actual constant speed. For example, m could be 60 miles per hour, where delta x is 2 hours. 60 miles per hour times 2 hours gives you 120 miles for the change in the distance. You can also think of that, of course, as delta y divided by delta x equals m, which is the equation for the slope when delta x is non-zero. All right, that's not too hard. Let's go to the exponential functions. That's harder. Here's the part that we looked at in the last video and we proved. If f is an exponential function, say f of x equals a times b to the x, then the relative change in y, delta y over y, equals b to the delta x minus 1. Okay? For fixed delta x, that's always going to be the case, no matter what starting value of x you pick. The relative change of y is constant for fixed delta x. All right? An equivalent, but perhaps more complicated way of thinking about it is to look at it this way, to say ultimately that delta y is proportional to y for fixed delta x. So if you've got an exponential growth graph, the higher you go on the graph, the bigger the change in y is. And in fact, if you double the height, you're going to double the change in y for a fixed delta x. I wrote some new stuff here. I hope you're writing this down. If not, pause the video for a second and write that down. Here's some new stuff that I wrote that is going to be more directly related to calculus. And we do want to inch ourselves more toward calculus here, since this is quick precalculus review. Look at what I have here. Finally, we can divide both sides of the last equation by delta x when it's non-zero. By last equation, I mean this equation. to get this equation. Think about that, compare it with this equation here. Delta y divided by delta x equals b to the delta x minus 1 divided by delta x times y. You can think of that as telling you that the rate of change of y with respect to x for a fixed delta x, that's this slope, which is really the slope of something called the secant line between those 2 points, is also proportional to y when delta x is fixed. Okay, think of delta x and b as fixed, so that this is a fixed number, and if b is bigger than 1, it's going to be a positive number. The slope of the secant line, the rate of change, the average rate of change of this function over this specific interval from x to x plus delta x is proportional to y as well. The higher you grow on the graph, the higher the slope is going to be, and in fact if you double the height y, you will double the slope of the secant line for a fixed delta x. The really interesting thing that gets invested in calculus is that the value of this proportionality constant when delta x is small is amazingly approximately equal to natural log of b. If you know about logarithms, you know what that means, hopefully. And this approximation gets better and better as delta x gets closer and closer to 0. ln of b is the natural log of b, log base e of b, where e is an irrational number like pi is. It's a special irrational number. It's approximately 2.71828, but its decimal expansion goes on forever without a repeating pattern. This is true, and I want to finish this video by illustrating that in this code up here. Let me add some things to this code. First, we'll add a line to give us the value of b to the delta x minus 1 divided by delta x. Let me put this in a fraction. Let me go ahead and put this part in a fraction. I'm dividing it by delta x. And what I just said was that that quantity should be very close to the natural log of b when delta x is small. Let me replace this now by an ln of b here. Unfortunately, here I can't replace that by an ln of b because that's not a built-in Mathematica command. Somewhat paradoxically, Mathematica represents the natural log as log, which many people represent as the common log, log base 10. But no, in Mathematica, the default for log is natural log, log base e, for reasons I won't get into. So instead of typing ln of b here, I need to type a capital log of b. That's going to be the natural log of b. Let's see if this happens. Are these two quantities close when delta x is small? Well, they're fairly close there when delta x is 1. What happens when delta x gets smaller? They get closer and closer together. For example, when delta x is 0.1, the value of this fraction is 0.183994, and the value of ln of b is 0.182322. And it doesn't matter what b is. I can change the value of b. These numbers are going to be relatively close together and get closer and closer together if delta x is smaller and smaller. If b is bigger, they're a little further apart. I'd have to make delta x even smaller to make them closer together. But they are always pretty good approximations here, no matter what b is. Okay, and that's what I'll end this video in this unit on.